I don't know if there's. Where did you say the audio checkbox was?
Oh, okay. So when you share, so just unshare your screen,
Yep.
and when you press on the green share button,
Oh,
down in the
got it.
bottom left hand corner, it's share sound. I think it's called.
Yep.
If you click
Thanks.
that and reshare, it'll sound us up.
Cool. And we've got a video to present. All right.
Away you go. Thank you.
Deriving the volume of a sphere. To figure out the volume of a sphere, you can try to tackle it by building up the shape using disks. Imagine building a stack with small CDs on each end and CDs that get larger towards the middle. Hopefully, if you did this, you'd end up with something ball-shaped, and you'd have your own approximation of a sphere. Though of course, if you ran your finger over the surface, you'd notice the jagged edges of the CDs and the grooves along the surface of the sphere. So what if you use card instead, or paper, or public toilet paper? With each thinner disc, the grooves get smaller and the shape feels more like a perfectly smooth sphere. So, to get the exact volume of a sphere, our approximation will take shape by using the volume of infinitely thin discs some infinitely many times, but only between the bottom of the sphere, z equals negative r, and the top, z equals r. We do this by integration. We'll multiply the radius of each disc, which follows along the edge of a semicircle, by their thickness, which we'll call dz. By following the fairly standard process of integration, we arrive at the well-known volume of a sphere, 4/3 pi r cubed, and we can see that disk or slice stacking is a suitable model for calculating volumes in 3 dimensions.
Now that we have covered the derivation of the formula for the volume of a sphere, we will now look at the formula for the surface area. There are several methods to derive the surface area of a sphere. There is not enough time in this presentation to go through all of them, so we will be just looking at integration. Other methods we could use include approximating the sphere by constructing pyramids with a common vertex of the center of the sphere, or using Cavalieri's principle to show that the surface area is equal to the area of the curved side of the smallest possible cylinder in which the sphere can fit. Like volume, we can find surface area by imagining the surface of the sphere being made up of many rings of different diameters stacked on top of each other. We can see that the circumference of each ring is given by 2 pi x. The height is given by ds, and so the surface area of each individual ring is given by 2 pi x ds. Now, we cannot integrate 2 pi x using ds, so we must get both variables in terms of another intermediate variable, in this case theta. We can see from the diagram that x is equal to r sine theta, and from the formula for the length of an arc, we get ds equals r d theta. So now we have the surface area of each ring being 2 pi r squared sine theta d theta. Therefore, the total surface area of a sphere is the integral between 0 and pi of 2 pi r squared sine theta d theta. Since we are taking r as a constant, we can take 2 pi r squared out of the integral, leaving just sine theta. The integral of sine theta is negative cos theta, and evaluating that between 0 and pi gives us 1 minus negative 1, which is of course equal to 2. This then gives us our final result for the surface area of a sphere, which we all know to be 4 pi r squared.
Relationship between volume and surface area. By means of simple differentiation, we see that the expression for a sphere's volume is transformed into its surface area. We can better visualize this representation by imagining a sphere of radius r, whose volume we wish to increase by slowly adding a layer of paint to its surface. The thickness of the added paint is represented by dr. From there we can represent our volume as dV, change in volume, equal to the surface area multiplied by the change in thickness, dr. Then through integration of both sides, our result is the equation for the volume of the sphere. What about for other surfaces? Does deriving the volume yield the result of surface area? Let's see. The cube, cylinder, the pyramid, and the cone. Clearly we can tell that the sphere is an outlier in its property of deriving the surface area from its volume. Why is this? Out of all the shapes in existence, the sphere is a perfect object. No bumps, bruises, or imperfections on its face. Able to travel for infinity along its surface without a hitch. Could this be its key to uniqueness?
A hypersphere is simply a 4D sphere. We can visualize this by moving the z-axis to the same plane as the x and y axes, and inserting a w-axis to signify this fourth dimension, as per the GIF on the left. Using the same method for deriving the volume of a sphere to derive the hypervolume, our slices are spheres with radius square root r squared minus w squared. We then integrate the volume of a sphere between negative r and r and substitute the r sphere value in. Utilizing integration by parts, trig identities, used substitutions, and a lot of hard work, the hypervolume turns out to be equal to half pi squared times radius to the power 4. As discussed earlier, by considering volume to be surface area multiplied by the change in radius, we can differentiate the hypervolume with respect to r to give hypersurface area equal to 2 pi squared times radius cubed.
So what about an ellipsoid? You could say its shape is similar to a sphere in terms of their round nature, but how are they actually related to one another? Given the volume of a sphere, 4 on 3 pi r cubed, you can see it is only dependent on its radius r, as the set of all points on the sphere's surface is equidistant from its center. But this is not true for an ellipsoid, and so its volume depends on the length of its semi-principal axis given by a, b, and c to give the formula 4 on 3 pi a times b times c. So visually, a sphere can be viewed as a special type of an ellipsoid, where the length of the three principal semi-axes a, b, and c are all equal. And because an ellipsoid is dependent on these three lengths, we will see on the next slide that this makes its surface area much more difficult to calculate than for a sphere. So the general formula for the surface area of an ellipsoid is already quite complicated, especially when it involves incomplete elliptical integrals E and F, which cannot be expressed simply using elementary functions or basic functions. So one of the alternative methods used to calculate the surface area of an ellipsoid is given by Knudd-Thompson's formula, which gives the surface area as an approximation with the least relative error, and the value of p is approximately 1.6075.
That's it. Yep.
Yeah, very good.